My name is Pavel Galibarov. I'm going to be your host for today, and our presenter is Marie Ohlsson from Swedish Winter Sports Research Center from the Department of Health Science in Mid-Sweden University. So first of all, I will give you a brief introduction to the system, to the antibody modeling system. I will explain what it is. And after this, we will switch to the actual presentation of today. And after this, we will have a short Q&A session. So first of all, let's start with a brief introduction to the antibody modeling system. So antibody modeling system is a software that allows you to do a musculoskeletal simulation. And what is a musculoskeletal simulation? This is a simulation of the human body, which is subjected to some motion and some external forces. For example, this is a motion that is recorded using some motion capture systems, and force play data is also given, and we apply it as external forces. After this, we provide all this input into the antibody modeling system, and as an output, we get internal body loads and all kinds of measurements such as joint moments, joint reaction forces, muscle activations, and so on. So this is a very detailed biomechanical model. There are many applications of the antibody modeling system in industry and research. One of the fields is quite big, and this is what we are going to focus today. It is sports. So you can analyze and possibly enhance the performance of athletes. You can design some training equipment. It is also used in orthopedics and medical device field. So there are many applications. Please visit our website and watch previous webinars if you're interested in this topic. It is also used in research for various applications. And it is also used in the automotive industry, and it is used for design of the car interior, and so on. Similarly, it can be applied in the aerospace for designing, for example, some training devices to be sent onto the space stations. A very hot topic right now is the assistive devices and exoskeletons, and you can see them as assistive devices, but they can be also resisting devices. So, for example, here you can see an example of an exoskeleton and a training device. And of course, this can also be applied in the ergonomics field for design of the furniture and workspace. As well as that, you can apply it in the design of consumer products. So whenever you have a human-centered applications, a detailed biomechanical analysis can be useful. So with that, I will conclude my short introduction to the antibody modeling system, and I will give the word to Marie.
Thanks for the introduction, Pavel. I will now present parts of my dissertation thesis, which I defended this spring. These parts includes musculoskeletal simulations in cross-country skiing and how they can further the understanding on muscle work and joint reactions. Here you can see a link to my thesis and also a reference to the paper that I will mainly talk about today. Cross-country skiing is an endurance sport. I will here show a small video from the sprint final in the Sochi Paralympics for men. Here, athletes with physical impairments of strength, range of motion, or spasticity, like, for example, leg amputation, cerebral palsy, or spinal cord injuries, compete. And all seated athletes compete in the same competition. And in this event, athletes' start time is determined by their classification. Classification is the structure that divides athletes into different groups, and it's there to ensure that athletes' impairment is relevant to sport performance. And classification has a large impact on creating fair competition, and therefore it's important that classification groups them into different classes depending on how their impairments affect their sport performance. And musculoskeletal simulations can answer where in the body muscle work is performed and thereby increase understanding of how different muscular strength impairments impact sports performance. Over to lower back pain and injuries. There is a high prevalence of lower back pain and injuries in able-bodied cross-country skiing, and then I mean standing skiing. We know also connected to lower back pain, there's a large risk connected to sitting, and there is a large risk for pain if you have a high peak anterior shear force and you have high compression over time between the vertebrae. And spinal flexion also results in high shear force. So all these three parts are connected to risk factors and lower back pain. And regarding this information, we can see in cross-country sit skiing, they are sitting. There's a high range of motion in the spine, flexion, extension. There are so many repetitions, just if you consider the training, which might be like 600 hours yearly, and then they're probably also seated in a wheelchair. So, but we don't know, there is no documentation about the injury rates connected to lower back pain in cross-country sit skiing. And shoulder pain instead and injuries, there is known that it's a large risk for people that are using wheelchair, that it's connected to risk. And subacromial impingement syndrome is common for people who are using wheelchair. And this syndrome means that the space between the head of humerus and the acromion arch, which I have noted as a red circle here, you can see in the figure, this space is reduced and thereby both the muscles and the nerves are compressed here, and this causes pain. And it's also known that a crouched sitting posture with a backward tilt of pelvis and a flexion of the spine can increase the risk of subacromial impingement syndrome. So these two athletes you saw in the film, they compete against each other, and often the high impaired athlete sits like the left picture with his knees higher than his hips, and the low impaired athletes sit with his knees lower than his hips. And it can also be low impairment, can be in leg amputation and full control of hip and trunk muscles, compared to the left picture, which might have a high spinal cord injury, which have caused paralysis in back extensors and abdominal muscles. I will name these knee high and knee low and use the abbreviation KH and KL a lot during this presentation. You can see here in the figure that the KH, knee high position, has a more flexed spine curvature, as you see with the line there in the red, compared to the more straight spine in knee low, and a larger flexion extension pattern on the spine. So therefore, we hypothesized that there is a risk of injuries in the lower back and in the shoulder connected to the sitting position knee high with this flexed spinal posture. And we don't want to injure the para-athletes more. Although the knee-low sitting position cannot be used by athletes with high paralysis, high impairment, as I said, for example, paralysis in the abdominals and the spine extensors, that's a reason why they sit with the knees higher than their hips. So therefore, we enabled the knee-seated posture for athletes with reduced trunk muscle control by creating a new sitting position with a more straight spine. And this was made by including a frontal trunk support, as you can see as an example here with the red lines in the right figure. And according to this background and these two sitting positions, the aims were to explore the difference between the sitting positions knee high and knee low for performance, spinal flexion, muscular power, joint reactions in the lumbar spine, and joint reactions in the shoulder. So the design, we tested these two positions in a laboratory on actually a double polling ergometer with 5 able-bodied female participants. They were national class cross-country skiers. The tests were separated by a minimal 48 hours, and they performed a submaximal incremental test, which means that they had 3 minutes and then a 1 minute rest and 3 minutes again on a higher intensity, like a stair. And we report results here from the exercise intensity 37 watts, where the blood lactate concentration was approximately 4 millimoles per liter. They also performed a maximal time trial for 3 minutes, where the purpose was to go as far as possible and in the end get the highest mean power output during this period. And there were 4 polling cycles during this 37 watts, and during the maximal trial were analyzed biomechanically. And over to simulations. I used the musculoskeletal simulations using the antibody modeling system, and as Pavel introduced you in the beginning, with the input of kinematic data from a 3D motion capture system, the quality system, and we measured pole forces right under the handle with strain gauges, linear strain gauge sets. And we obtained the muscle forces and the joint reactions. And you can see the marker system in the figures, which is a little adapted from the Helen Hayes model. To the modeling part then, we used the full body model from the model repository, version 1.6.3. This is a full body model which comprised 31 rigid bodies and around 700 muscle parts. And for each participant, a model was constructed for both sitting positions, and the model was scaled according to height and weight of the participant, and then with this length, mass, fat scaling routine in the software. We used a simple force muscle model, and the lumbar spine was constructed of 5 vertebrae with spherical joints in between and intra-abdominal pressure as described in the SEA 2007. And also a lumbar spinal rhythm where, because we had markers on pelvis and thorax, and then these markers defined how the motion were divided between the lumbar vertebrae, so less motion further down. This model has been validated in the lumbar spine by Bassini and showed good agreement with a similar motion capture marker set as we have utilized here, and showed good agreement with measured direction forces. And for the glenohumeral joint, the shoulder joint, which was a spherical joint between humerus and scapula, the computed forces has been verified with a quite good accuracy to measured shoulder reaction forces by Sylvain Kaub. And over to more about modeling. Because the sit ski, even though it's made of steel and aluminium in this case, it's not completely rigid when you start to do high endurance exercise, and the human body is not so completely rigid either. So it took a little handicraft to actually build the constraints between the body model and the sit ski. And we utilized both hard constraints where no motion was allowed between the body model and the sit ski, and also soft constraints where motion were allowed The soft constraints were created by the dynamical contact model, consisting of a contact point on the body model and a contact zone on the sit ski. And you can see the gray boxes, hope, in this figure. For the KL sitting position, there is a gray cylindrical box at the frontal support between thorax and the sit ski. And for the knee high, the KH sitting position, there is a gray cylindrical box under the seat and on the backrest, and also there are one in each knee connecting the support under the knee to the sit ski in between there. And then over to the muscle recruitment criteria. To solve the overdeterminant mechanical system, that we have more muscles than degrees of freedom in the joints, we used a fifth order polynomial muscle recruitment criteria. And this was chosen to be a trade-off between a second order and an infinite order polynomial based on higher validity for the compression forces in the lumbar spine, which showed earlier, and a higher level of cooperation between muscles because we had so high intensity endurance exercise. And over to muscular power. Because muscular work costs more metabolic energy for concentric contraction, shortening of muscle fibers, compared to eccentric contractions, lengthening of muscle fibers, we used an estimate for the total metabolic muscle power. So the first row in this upper equation is connected to eccentric muscle work, and the second row is connected to concentric muscle work. And then all the muscles, muscular metabolic power, are summed up into a total, and this was, as I said earlier, an average over 4 cycles that we analyzed for the 2 exercise intensities. So over to the results. The results showed higher performance was achieved in the KH sitting position. And by performance, we here mean that we had the highest power output during the maximal intensity trial, divided by body weight, because in cross-country sit skiing, you have to transport your body around the track. So therefore, we made it in that way. And you can see the numbers up there. And here you also see a visualization of one participant during the 37 watts exercise, left with the frontal support and right with the knee-high sitting position. And you might see there is a little more activation in the muscles. They are shown a little darker red around the shoulder for the KL position. And if you look into the right figure, the KH position, there is a little more activation in the trunk. And the blue lines that you see coming out from the shoulder when she pushes, that represent the shoulder joint reactions, and you can see both the size of them and the direction of them. To the kinematics and the pole forces, I don't expect you to see the numbers on my scales there, but the black line in the figures represent the knee-high, the KH position, and the gray ones connected to the KL sitting position. And there was a large range of motion and flexion of both spine and hip for KH, knees high sitting position. And we also saw that the pole force, the axial pole force, had a smaller peak during the 37 watts exercise, but there was no different during maximal. To the joint reactions then, I will start with the lumbar joint reactions. And this was between the lumbar vertebra 4 and lumbar vertebra 5. And the results are presented as normalized to the joint reaction forces of a theoretical standing position for each participant. So we took the scaled model from the sitting and made that model in the computer to stand up and used the exact the same joint angles for all the different models. And then we took that joint reactions and normalized with the results we got from the sitting results. So you can see the values of the highest up to 10 times higher than the reactions of standing. And this we did, the normalization we did to because they had different, the participants had different weights. And the results, the knee-high position is connecting to the black bars also here. They had a larger spine flexion, as we saw in the last slide. And here we can also see that the knee-high position was connected to higher compression force and anterior shear force, especially during maximal, but also tendencies during the submaximal exercise, 36 watts. So these results was in line with our hypothesis that spinal flexion were related to larger joint reactions in the lumbar spine. For the shoulders, we hypothesized that larger spinal flexion would induce higher shoulder joint reaction forces, and that would then be in KH, knee high. But actually the opposite was shown. The KL position, the gray bars, showed larger peak and mean force when power output was similar as in 37 watts. During maximal exercise, the power output was higher for knees high, KH, and but there was no difference in the shoulder joint reactions. So therefore, it was concluded that for similar power output, shoulder joint reactions were higher for the KL position. For the muscular metabolic power, this study showed that cross-country sit skiing were driven by arm and shoulder muscles power in general, both sitting position mostly. But the results also showed that the knee-high, the KH sitting position, had less arm power and slightly more from hips, legs, and spine muscle involvement. And then summing up the results, the KH position showed higher performance, larger spinal flexion, higher shear force, anterior shear force between lumbar vertebra 4 and 5, and also higher compression force. And the KH position also had larger involvement of hips, legs, and spine muscles. Over to the KL position then, the knees low, had larger shoulder joint reactions and lower performance, larger arm muscle power. I want to mention some limitation of this design. We used, for this part that I present here, we used able-bodied participants, and the movement pattern might be different for athletes with impairments, and hence also the reaction forces might also be a little bit different. But I want to mention that it's not easy task to perform different sitting positions of people with impairments. I've done one test with an athlete with high paralysis, and it took a lot of familiarization time because I wanted to ensure that that athlete was not injured during my tests, and the injury risk of shoulders, or lumbar back or pressure source when I put him into a completely new seat. So, but I haven't done any simulations regarding those positions, but it's possible for a athlete with paralysis in abdominal and back extensors to do these sitting positions. It's also maybe a low number of participants. I only have 5 participants, which is considered quite low to be in sports science, but maybe it's quite okay to be in the simulation world, I would say. And so to 3 dots that I want to conclude from the results I have presented here, and that the knee high, the KH, with larger flexion of the spine might indicate higher risk of lower back pain injury. And this is in line with the background that I presented, that spine flexion is connected to higher shear force. And even if you don't have you don't sense this area in your body because you have a paralysis, it's still dangerous to get a disc herniation, for example. So it can still be interesting to understand the joint reactions if you have a paralysis also. For the shoulders, larger shoulder reactions was obtained when shoulder muscle power was larger. The hypothesis in this study was that a larger spinal flexion would have caused scapula to somehow rotate forward and downward in the sagittal plane, if you would see it from the side, and thereby depressing the acromial process onto the glenohumeral joint, and thereby reducing this subacromial space, which I showed you in the beginning with this red circle, and in that way have increased the joint reaction force in the shoulder. But the results showed the opposite, that a lower spinal flexion were related to higher values of shoulder joint reaction. And it might be possible that the shoulder model was a little too simplistic to capture the impact of the spinal flexion on the shoulder, because this modeling did not include any contact model between acromion and humerus. So therefore, I don't want to say anything about if one sitting position is favorable regarding the risk of shoulder injuries. And to the last dot here on my slide, most muscular metabolic power was produced in the arms for both position. It's an arm-driven movement to be seated and do double pulling. But the knee-high KH position was relatively more driven by spine and hip and leg muscles. And this might be useful for classification because musculoskeletal simulation can estimate where in the body muscle work is performed and thereby increase understanding how different impairments impact sports performance. Therefore, I think the method of musculoskeletal simulation has the potential to contribute with information for development of classification systems in parasport. They won't solve the problem, but they might give some information at least. Thanks for listening. Now we have time for some questions. I think I need some help from Pavel to be able to do that. And thanks so much.
Yes, thank you very much, Marie. That was a very interesting presentation and very educational at the same time. So I have my next slide. First of all, I would like to say that if you have any questions, please submit them to the question box. We will answer them in a second. But at the moment, I will give you some information. So here on the screen, you can see a couple of links. So the first one is our YouTube channel. So you can find previous recorded webinars, and they cover quite a wide range of different topics. So you can find all the fields that I described in the beginning. Please visit our website. So You can find the events that Anybody Technology attends and the dates related to those events. You could also find a list of publications, and you can read everything about what our customers have accomplished, and there are quite a lot of interesting publications out there. And I would like to bring to your attention that we will be present at the Intelligent Robots and Systems conference in Madrid, starting from 1st of October until 5th of October. The booth number is number 80. Please feel free to visit us. And right now we are going to start with the questions and answers. Just give me a second to read some of the questions, and I will read them for Marie. So I have a question. Marie, could you explain further why the trunk was held into a specific position in the knee low condition?
That was because we wanted to make a sitting position that was intended for athletes with high impairment, like for example paralysis in the trunk and in the spine extensors, in the abdominals. So we wanted to compare the knee-high position, which they normally use, to a position that they can use, but they can't use a knee-low sitting position without the support. So thereby we constructed a new sitting position. And I have also tested this for a para-athlete with this paralysis, so it works, but I have not made simulations of that.
Okay, thank you very much. I have another one. Have you measured peak torque values for the shoulders in each position?
No, actually I have not. I've just looked to the reaction forces. Maybe that's a good idea.
I also have a question regarding how the results could help the classification. I think, could you elaborate on that?
Yeah, it would be interesting to really to see how, if I have a standardized motion that we think this is in cross-country skiing, they normally do this motion. And if I remove muscles, what will happen? And to compare that. But it's also interesting, I think, to understand how much is really the abdominals helping, or how much is the pectoralis helping, for example.
Have you considered the seat position angle in knees low position, and does it have an effect on performance markers?
Once again, please.
Have you considered the seat position angle in knee low position, and what are the effects on the performance markers?
No, I have not tested different. I mean, you mean hip angles connected to where the knees are placed? No, I have not done that. I have done a simulation connected to knee low without a trunk support also, but not for five athletes.
Okay, I have another question. As I understood, the athletes who are in the knee high positions, they start first.
In this sprint event, they start a number of seconds before, but in a distance run, it's a percentage system. So the result time times a certain percentage factor, then you will get the result list, and the percentage is different depending on your classification.
Okay, so I just heard from you that the power output in the knee high position was a little bit higher. So in a way, that would also help a little.
Yeah, maybe, but we have to consider that this was made in an indoor, in an ergometer in a lab. So if we want to have a system outside that works both uphill and downhill and different distances, it has to be more research done behind that.
But that is very interesting. I think that is it for today. We don't have any questions. Please contact us if you have any further questions and you would like to discuss something. But with that, we would like to conclude this session. We thank you very much, Marie. That was very interesting and very educational.
Thank you so much for having me here. I'm glad.
And just a small reminder that we will put this presentation on YouTube channel, so please see it again if you would like to. And we will also share some of the slides with you. So thank you very much and have a very nice evening.